Hello and welcome. For this video we are looking at the idea of polymers, and this is for GCSE Chemistry Unit 2. Now you will remember back from Chemistry Unit 1 about polymerization, and we talked about how it happens, and we had an example of a substance that came from crude oil. This was a substance called ethene, and we learnt about how ethene could become attached to other ethene molecules through a reaction, and you'd get a long chain of ethene molecules, or ethene monomers as we called them, and we'd end up with a substance called polyethene. And this was a type of plastic, and it could be used for various things. What we're going to look at today is the features of different types of plastic, including high density and low density plastics or polymers, and we're also going to look at thermosetting and thermosoftening polymers and why they have certain features. Now it all gets very complicated if I try and draw everything with the molecular structure like this, so I'm just going to go and draw them as blocks. So each one of these represents a monomer. In fact, I'm going to go one step further, simplify it even further, and just draw it as a line. Now what you should remember is this line represents a chain of monomers. In this case it's ethene, and that links all back to polymerization, and this you don't really particularly need to know the details of for this exam, but if you're interested you can go back and look at that video and see how all that works. Okay, so when I draw these lines, it's more complicated than just a bunch of lines. You have to remember they're polymers made of each of these kinds of individual units called monomers. Okay, so here we have a polymer, and in this particular example it's polyethene, and we can make different types of plastics out of it, and the way we do that is we do reactions in different conditions. So if you go through one type of reaction, this would be having a very high pressure, very tiny traces of oxygen, and you would end up with what we call low density polyethene. And the key thing about polyethene is that we have all these branches, and the branches link together in this particular way, and you can see that all the polymer chains are quite far apart, and so we say it's low density polyethene, and this has a lower melting point, and it's a little bit softer than the high density, which we're going to look at. You don't need to know the details of exactly how this happens. All you need to know is that one set of conditions can create low density, and the key thing about low density is that the chains are in branches, and that separates the chains out a little bit, makes it low density, gives it a lower melting point. And under a second set of conditions you could get high density polyethene. So the conditions for this are a slightly raised pressure only, and at 50 degrees, and using a certain catalyst, but again the details of those are not important. The point is that if you create this with slightly different conditions, you get high density polyethene, and this has a slightly higher melting point, and it's a slightly harder polymer. And the reason why it's high density and harder is because of the way the polymer chains are arranged. They're much closer together, and therefore the forces of attraction between them are slightly stronger. So key and important point here: forces of attraction for the low density polymer, the forces of attraction are weaker here because the chains are further apart, and here the forces of attraction are stronger. So you'd end up with a slightly higher melting point, and it would be a slightly harder polymer, or a slightly harder plastic. Okay, but the key thing is this here: you should be able to talk about how the chains are arranged and the force of attraction between them. Okay, so the next thing I want to look at is this idea of thermosoftening and thermosetting polymers, and they are basically, why is that there? I don't know. They are basically chains of polymers, as we've spoken about before, but they're arranged in a slightly different way. For thermosoftening polymers, you can see that the chains are fairly tangled together and not in a sort of rigid or regular structure, and the result is that the chains are fairly easy to separate. So these chains here, easy to separate, and therefore thermosoftening polymers or thermosoftening plastics can melt, or can be melted quite easily, and this makes them ideal for recycling and that sort of thing. What sort of substances are made? Well, we have kind of things you find around the house: plastic bottles, containers, containers for your milk, that sort of thing, and all this stuff can be recycled. On the other side of things, we've got these thermosetting polymers. Now, if you notice, these polymers have long chains. They're in a slightly more regular shape, and you'll notice these little cross linkages between the polymers, and these cross linkages are actually covalent bonds. And these covalent bonds are strong, and you have lots of these which will link up the different polymer chains. So what you have is these polymer chains which are very close together, but they also have these very strong covalent bonds that hold them together. Whatever you do, don't get covalent bonds mixed up with the intermolecular forces that we were talking about. That's not the same thing. These are bonds between the actual polymer chains, and makes the thermosetting plastic or thermosetting polymer very, very strong, and it also makes it very hard to melt. In fact, these things won't melt, they burn before they melt. Okay, so what kinds of things are these used for? We have cooking spatulas. You can imagine you don't want your spatula to melt while you're frying your eggs, so that's made of thermosetting polymers. We have pan handles, which we don't want to melt if they get hot, and plug sockets and plugs, things like that, are made of these thermosetting polymers. Thermosetting polymers cannot be melted and remolded, whereas thermosoftening ones can be melted and can be remolded. And that means, again, for recycling, that's really good. But for these, once they are made, once the cross linkages or the covalent bonds are there, that's it. You can't actually melt them anymore. Okay, so the two differences are that we have thermosoftening with polymers that are easy to separate because of the fact that they're not held together strongly, and thermosetting polymers which have strong covalent bonds holding the chains together. Remember not to mix up covalent bond with these intermolecular forces. Now, the last thing I want to go through is actually for the higher tier. This is all for the higher tier, and you should be able to explain why thermosoftening polymers are easy to separate out and why they can melt. And really, I've highlighted it down here for you. We've got weak intermolecular forces of attraction. Okay, again, don't mix these up with covalent bonds. So there are forces of attraction between the chains, but they are very weak, and that means the polymers can separate more easily at lower temperatures. And another way to say that really is less heat energy is needed to separate the polymer chains. Okay, so you should be able to talk about thermosoftening polymers, why they are easier to melt in this way here, and these are all the key words and the key ideas that you should be able to talk about and write down if asked in an exam. Okay, so that's an overview of the topic of polymers and so on, and thank you for watching. I'll see you again soon.